Good day, everyone. Our topic for today is about logical equivalence. This is the lecture 2 of ComSci 56. So let us move on. In the previous lessons, we have talked about propositions, conjunction and disjunction, exclusive or, and implication, converse, contrapositive, inverse, which are derivatives of implication, as well as compound the statements and how to obtain the truth values of several compound statements. Okay, so for this topic, we will talk about logical equivalence. So consider these two statements. 6 is greater than 2 and 2 is less than 6. So we can say that these two statements are the same. Okay, and these are two different ways of saying the same thing. Okay, so these are both true given the definition of greater than as well as less than. Meanwhile, these two statements, dogs bark and cats meow, and another statement, cats meow and dogs bark. So this first statement is true, okay, because dogs bark indeed, and cats also meow. On the other hand, another statement is just an interchange version of the first statement. So we just interchange the statement 1 and statement 2. Okay, so this is cats meow and dogs bark, which is also true. So basically, these two statements are the same. Okay, but the reason has nothing to do with the definition of words, but the way you have structured the sentence. Okay, the reason has something to do with the logical form of the two statements, which make them similar or have similar meaning. And now let's examine the truth values of the statements. So let's say P is dogs bark, Q cats meow, and P and Q is dogs bark and cats meow, and Q and P will be cats meow and dogs bark. So let us try to prove that these two statements, P and Q and P, are indeed the same or have similar meaning using a truth table. Okay, suppose we have two distinct statements or variables P and Q. Since we have two statements, the possible combinations are 4. Okay, if P is true, then Q could either be true or false. If P is false, then Q could either be true or false. Now, let us examine the truth values of P and Q. Okay, so by the definition of the conjunction operator, it will only be false. It will only be true if both statements are true. Okay, that means that if P is true and Q is true, then P and Q will be true. Otherwise, false. Okay, so now for the first row, P is true and Q is true. So that means that P and Q is also true. And then for the second combination, P is true and Q is false, so it will be false. So similarly, for the last rows or last combination of truth values, there is at least one false, which will cause this conjunction of P and Q to be false. Okay, now let's try to examine the truth values for Q and P. Okay, so now let's look at the values of Q and P. So similarly, since this is using a conjunction operator, so this will only be false if this will only be true if both Q and P are true. Okay, if Q is true and if P is true, then this will result to a true, otherwise false. Okay, so now true and true, so that will give us a true, false and true. That will give us a false. Similarly, for the last two statements, there is at least one false, which gives us a false na outcomes. Now, we can see that the outcomes for P and Q and P are the same. Okay, this for the first na row, if P is true and Q is true, then P and Q is true. Similarly, Q and P is also true. And for the rest of the combinations of P and Q, P and Q and Q and P are similar. Okay, so this is the same, this is the same, this is also the same. So now we can say that P and Q and P are logically equivalent. Okay. So by definition, if two statements P and Q are logically equivalent, they have the same truth na values. Okay? For all combinations of truth values of the statement variables occurring in P and Q. So we denote the logical equivalence of P and Q by this symbolic notation. Okay, we will use this symbol. So going back to the previous slide, so we can say that P and Q is logically equivalent to Q and P. Okay. So let's have our first example. So let us show using a truth table that P implies Q is equivalent to not P or Q. Okay, so since we have two distinct variables P and Q, so we similarly have four the combinations of truth values occurring in P and Q. Okay, now let us try to determine the truth values for P implies Q. Okay, so P, by definition of the implication, this will only be false if P is true and Q is false. Okay, so that means that it will be false at this row or at this combination if P is true and Q is false, and the rest will be true. Okay, now let us try to examine the truth values of not P or Q. Okay, so let us first check the truth values for not P. So not P is simply a negation of P. Okay, so we take the opposite na truth value of P. So if P is true, then not P will be false. If P is false, then not P will be true. Now, let us take the conjunction or the disjunction, disjunction of not P or Q. Okay, so we have not P or Q. So, by the definition of the disjunction statement, this will only be false if P and Q are both false. Okay, so P, not P or Q. So true and false, that will give us a true. False and false, that will give us a false. Since two statements are both false, so true and true, this will give us a true, and false and true, that will give us also a true. Okay, so now let us check if if these statements P implies Q and not P or Q are logically equivalent. Okay, so to do that, if they have the same values, then we can say that it is true. Okay, so we can use this notation. P implies Q is logically equivalent to not P or Q, or it should actually be biconditional. Okay, because they should have the same values. Okay, now if P implies Q is true and not P or Q is true, so that is also true, meaning this will be true. And then they are both false, so this will give us a true. Then they are both true if P is false and Q is true, so that will also give us a true. And on the last is these two statements have the same true values, so this will also give us a true. So since this gives us a tautology, the equivalence that we can say that these two statements are logically equivalent. Okay,